Try to find the right button. There we go. We are working and we're going to finish today on limits at infinity, and I'm going to show you the techniques by just doing some more examples of finding limits at infinity. And we've talked about how to do it numerically, right? And we're going to look now at essentially the technique is you divide the top. Well, we've done numeric and we've done brute force, but we're now going to look at, in particular, dividing the top and bottom by some power of x, right? So let's pick one. Let's suppose you want to define the limit as x tends to infinity. So that's the limit at infinity, or something like x cubed plus 2x. And on the bottom, it would be 3x cubed minus x squared. So that would be an example, right? Put a plus 1 in there. There we go. Now, what you do in these questions, these situations, is you divide the top and the bottom by a power of x. If the biggest power of x here is x cubed, and the largest power of x here is also x cubed. So in this case, you divide top and bottom both by x cubed. And then you go through each one of the terms one at a time. And you divide that guy and you get 1. And you divide that guy and you get 2 over x squared. And you divide that guy and it's 3. This guy gets you negative 1 over x. And this guy gets you 1 over x cubed. Are you comfortable about all 5 terms when they're divided by x cubed? These are the guys that you get. Are you comfortable with how I got all these pieces? We good? Now, once you've done that, you essentially do brute force. That means you make x infinite and you see what you've got. And we have rules about what you get when you make x infinite. So in this case, it's 2 over infinity squared. 3 take away 1 over infinity plus 1 over infinity cubed. Right? So far, so good. Now, what number is 2 divided by infinity or infinity squared or infinity cubed? 2 divided by any kind of infinity. What do you get?
0.
You get big fat 0. And for the same kind of argument, don't you get take away 0 plus 0? So you see here, the final answer is 1/3. So we now know that the limit as x tends to infinity is 1/3. If you put that into Desmos and you looked at it, what you would find is that it has a horizontal asymptote at y equals 1/3. And I don't quite know what's going on here, but what I know for sure is, doesn't it flatline like that? In other words, as x gets larger, the y value, right? The value of this expression is its y value, tends to 1/3. Are we cool with that situation, how you would do that, right? So I'm just trying to go through every permutation. There are tons of homework questions, so I'm not going to pick those. We'll let you deal with them. And let's do a x squared take away 4 on the top and an x cubed add an x on the bottom. Let's try that one. And when you do these limits at infinity, when it's polynomials like this, there's 1 of 3 answers you're going to get. You're going to get some kind of number, right? 1/3, 42. You're going to get 0, which is really just a number, or you're going to get some kind of infinity, right? That's kind of what's going to happen. So in this case, I have a choice. The biggest power on the top is x squared, and the biggest power on the bottom is x cubed. But I must divide the top and bottom by the same power, right? That's why it's allowed. And so when you've got a choice between x squared and x cubed, right, as we have here, I suggest you always pick the smaller of the 2 powers. You can actually pick either, but to me, the math is easier if you just pick the smaller of the 2. And so that's the only reason I'm picking x squared, because I think the math comes out nicer. And then I'm going to divide everybody by x squared. So that guy's 1. That guy is 4 over x squared. That guy is x. Oops, that's an x. And this guy is a 1 over x squared. Now let's see what happens when we do brute force. 1, take away 4 over infinity squared. Infinity, add 1 over infinity squared. Would you agree that the top line is 1, take away 0, which is 1? Are you comfortable with the 4 over infinity gets you 0? Now, 1 over infinity squared gets me 0. And so I've now got infinity plus 0, which is infinity. And what does 1 divided by infinity get us?
0.
0. So remember I said there's 3 combinations. The first one is a number. This would be an example of it, right? The limit is a number, it's a third. The second situation is that the limit is 0. Do you see the math of how that turns out, right? 0. We've done that. And if you did a sketch of this, what you would find out is that as x gets really big and positive, it gets closer and closer to the x-axis. In other words, its y value becomes almost 0. So that's what the limit for that one is. So there's one left, isn't there, where the limit is infinite? Right, that could happen. Let's show you a question where that's what does happen. So you have a limit as x tends to infinity, and it's going to be x to the 4 plus x squared plus 2. And on the bottom, it's going to be x squared plus x. All the questions I'm doing right now have polynomials, right? X cubes and squares, top and bottom, right? So this is the third situation. This is going to be infinite. But let's find out why. The biggest power on the top is x to the 4. The biggest power on the bottom is x squared. So far, so good? Right. What do you divide the top and bottom by in this case to keep the math easier?
X squared.
Pick the smaller, pick the x squared. If you want to do the x4, go ahead and see what happens. It does work, but it's much uglier, in my opinion. That guy is x squared. That guy is 1. And the third one is 2 over x squared. And that guy is 1. And the guy next to him is 1 over x. So now we can do the brute force. We have infinity squared plus 1 plus 2 over infinity squared. And 1 plus 1 over infinity. Right, so far so good. Okay, what do you get if you take infinity and square it? What should I write down?
Infinity.
Infinity. If you take infinity and add 1 to it, what do you get?
Infinity.
Right. So can I combine these two as a single infinity? You comfortable with that? I'm going to put the second guy as 0 and the bottom guy is 0. Now, infinity plus 0 is infinity, and 1 plus 0 is 1. And what does infinity divided by 1 get you?
Still infinity.
Still infinity. What does infinity divided by 22 get you? Still infinite, right? If a number is infinitely large, can't you divide it by a number like 4, 24, or 1,000,000? And isn't the answer still going to be infinitely large? So dividing infinity by any fixed number, in this case 1, but it could be 10 or 20 the next time, is still going to get you infinite. So the answer to what is the limit of this function as x tends to infinity, the answer is infinity. Are we good? So let me make the algebra uglier. Let's introduce square roots. You do get questions in the homework that do that. So the limit as x tends to infinity of x squared plus 2x plus 3 over the square root of x to the 4 plus 3x. Now, this is a little bit more difficult than the ones we've done. It's still going to be divide the top and bottom, but there's going to be a kind of check on this. Would you agree the top power is x squared? Agree? X squared. The bottom power isn't really x to the 4. And the reason it really isn't x to the 4 is, isn't it inside the square root?
Yes, that's right.
So it's really just worth x squared, isn't it? Because the square root of x to the 4 is x squared. So I'm going to divide the top and bottom by x squared, right? And I'm going to change the bottom x squared, and I'm going to call it the square root of x to the 4. Can you see why calling it the square root of x to the 4 is going to help with the math? Isn't the square root of x to the 4 just x squared, right? I'm just writing it down in a strange way. But the reason I'm writing it down is, won't it play well with this guy? If I just called it x squared, isn't there a temptation just to divide these two guys by x squared and get the math wrong? But if I call it the square root of x to the 4, I'm more likely to do the division correct. So when you see square roots, make sure that the guy that you're using it with is also a square root, right? So if that's square root, make this a square root. It still has to be equal to x squared, right? But it's written this way. So let's see. Question.
Could you just make the exponentials into fractions? So like x to the 4 over 2 plus 3x to the 1/2, and then still work with just x squared on both.
Oh, so you want to call this x to the 4 plus 3x to the half, right?
Yeah.
And you want to call this what? X squared?
So call it like x to the 4/2 plus 3x to the 1/2, and then make both top and bottom x squared they're dividing by.
I'm trying to see what you're getting at. So if I pick you up correctly, the bit that I kind of makes sense to me was that, right?
Yeah.
Now, and you want to divide by what then?
Just have them both be top and bottom be x squared, so that it's
Okay.
easier to work
So
with, 'cause you have just
what my problem is, how do you take this guy and divide it easily by that guy?
okay.
It's just, I mean, I guess you could do it, but if you wanted to do that, wouldn't you still have to call this x to the 4 to the half, in which case you're back to where you started, so you may as well just do it.
Okay.
Interesting thought. I mean, it might work. Now, this guy gets me a 1. You get that guy. And you get that guy. And this guy gets you 1. And that guy, ooh, you get him. Divide by x squared, and x squared. Divide by it because it's inside the square root, x to the 4, x to the 4. So far, so good. Now we can do brute force. 1 plus 2 over infinity plus 3 over infinity squared. That's the top row. And a little bit more awkward on the bottom. The square root of 1 plus 3 over infinity squared. On the top, that guy is 0, that guy is 0. This guy is 1 plus 0. Almost done. Top adds up to 1. The bottom is square root of 1. Well, isn't that just 1? So the limit of this guy as x tends to infinity is the number 1. Are we good? Do another square root. Let's put numbers in as well, just to make it a little bit more interesting. Let's do 4x cubed plus 2 on the top, and the square root of 16x to the 6 plus x on the bottom. And we want to know what the limit as x tends to infinity of that fraction is. Now we must make sure that divide the top and bottom by the same amount. I don't think we can argue. Would you agree x cubed's the guy in the top? It's an x cubed. What does that guy in the bottom equal? What's he the same as?
It's equivalent to x cubed.
Agreed?
We see the red.
So that means x cubed, and call this guy the square root of x to 6. So I'm now going to take each term now and divide them by some version of x cubed. Divide that by x cubed, you get 4. Divide this term by x cubed, you get that ugly fraction. And on the bottom, we're going to divide everybody by the square of x to the 6. So that guy gets you 16, and that guy gets you 1 over x to the 5. You agree the square roots are just uglier to work with, right? They're not as clean as they would be if it was just normal polynomials. I should be able to just plug in, right, brute force, and see what we get. Top row, 4 plus 0. Bottom row, square root, 16 plus another 0. 4 on the top, square root 16 on the bottom. Positive square root. Answer is 1 again. Any questions about the square root ones that we've done? And by the way, there's no reason why the answer should always be 1. It just happens to be what I'm getting right now. Could be 10 or a half, you know, anything could happen. Any questions about what we've done so far?
Are we assuming that square roots are always going to be positive numbers?
When they write a square root in this form here, we assume it's positive. If they wanted it to be negative, they have to put a negative there.
Okay, thank you.
Now, just since I've got that and it's an EV fix, can you imagine that that did have a negative? Good harm. Then this would be negative, 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 and the answer would have just been -1. Do you see, it wouldn't have made much difference to the math. Wouldn't it just make the answer a negative something instead of a positive something? I tell you what, why don't I give you one to try yourself, and that'll give me a good idea that things are going well. So here is the limit as x tends to infinity. You got 2 minutes. Find the limit of that ugly fraction. Be back in a moment. About 30 seconds left. Okay, what should I divide the top by? Let's start there.
X squared.
Right. And shouldn't you call the bottom the square root of x to the 4, which is x squared, but written in a form that's going to be helpful. And then you divide it, so you get 4 minus 1 over x plus 1 over x squared. And on the bottom, you've got a big square root, but inside it, you get a 36. And then you divide this guy, you get that. So once you've done all the divisions that you need to do, and the next step is pretty much standard, don't you then do brute force? Make everybody infinite, make every x infinite, and see what happens. Oops, don't need that anymore. So 4 take away 1 over infinity plus 1 over infinity squared. And square root of 36 plus 2 over infinity squared. Right, hopefully you got that far. Now, each one of these guys with the infinities turns into 0. So you get 4 take away 0 plus a 0 and a 36 plus a 0. So you're looking at 4 positive square root of 36, 4 over 6, which eventually became 2/3. Does that look like what you got? 2/3. Then I'm pretty comfortable for those who managed to do that, that you're good with these guys. Now, I've only shown you square roots where the answer was a number, right? There are 2 more combinations that we're going to do. Square roots where the answer is infinity, and square roots where the answer is 0. So let's show you what an example of each of those 2, and that will be us cover the square root situation, at least that type of square root. So let's do one that ends up being 0. So the limit as x tends to infinity of the, I'll put the square root in the top just because I can, x squared plus x, and on the bottom, we'll do x cubed minus 2. Right. The biggest power on the bottom is x cubed. Agreed? What does the power, the square root guy in the top, what power of x he is the same as? And it's not x squared. What power of x is the square root of x squared the same as?
Just x.
Just x. So that means I'm going to do this guy with that and this guy with that. I'm using the rule that if you've got a choice, don't you pick the smaller one? Isn't x smaller than x cubed? So I'm picking the smaller one. So we're now going to do the limit as x tends to infinity. This guy gets you 1, and the term next to it gets you 1 over x. This guy gets you x squared, and the term next to it gets you negative 2 over x. So that's what it looks like after you've divided the top and bottom by x or x squared. Now you do brute force. 1 plus 1 over infinity on the top, and infinity squared, take away 2 over infinity on the bottom. Okay. It's 1 plus 1 over infinity gets you 0. Infinity squared is just infinity. Take away 2 over that guy is take away 0. Do you notice all the 1 over infinities and 2 over infinities and things like that just get you 0? But infinity squared is still really large. It's still infinite. And the square root of 1 is 1. And now you have 1 over infinity. And 1 over infinity is actually, as a limit at least, isn't it a number? What do you get if you take 1 and divide it by infinity? you get 0. And I promised you that, didn't I say there's an example where it was going to be a limit of 0. Do you see how it works? How the math is similar, but you know the end result may be a little bit different because it's a different question. Right? So that's what a limit with a square root would look like if it ends up being 0. And there's one last possibility, and that is that you could get an infinite answer. Suppose we did this one. We're going to divide the top and bottom by some power of x. What does 3x squared plus x plus 1? And would you agree that the best power is x squared here, right? What does the top guy get you? What power of x is that square root equivalent to?
4.
Check again. Square root of x.
Square root of x to the 4. Are you saying what does the x squared on bottom become? Or
No, no. Oh, I'm asking what on the top.
Okay, x to the 3rd.
X to the cube, right? So there's a cube on the top and a square on the bottom. Doesn't that mean you always pick the smaller one, right? So I'm picking x squared. And the top one is still x squared. I'm just writing it down in terms of its equivalent version as a square root. So x squared is x square root of x to the 4. And now I can do the division part. That guy gets you x squared. That guy gets you him. This guy here gets you 3 plus 1 over x plus 1 over x squared. Are we comfortable with that? We've been doing quite a lot of them today where you divide by things. Should be able to do the brute force now. Infinity squared plus 2 over infinity. Infinity squared is still infinitely big, whereas 2 divided by infinity is 0. 1 over infinity is 0, and 1 over infinity squared is 0. So I have the square root of infinity on the top over 3. Infinity is a strange creature. You know, infinity squared is infinite, right? Infinity cubed is infinite. Isn't the square root of infinity also infinity? If you took an incredibly large number and you found its square root, isn't it still an incredibly large number, right? It's still infinite. So I have infinity divided by 3. What happens if you take infinity and you divide it by a number like 2, 3, or 43? Isn't it still infinite? So there is a limit of a fraction function with a square root in it where the limit was infinity. Here's an example of one where the limit was 0. And did we have it in there? And we did earlier the example of a limit where it was a number. So all 3 things can happen in that situation as well. Any questions? So hopefully if it's polynomials, right? X squared plus x on the top, x cubed minus 4 on the bottom, you've seen how to do those. If there's a square root somewhere, right? We've seen how to deal with those. So what is next? Well, I think the best way of describing the next is special cases, right? Situations that might not fall quite into the same category as the ones we've done. So here is an example of what I'm getting at. We want to find the limit of that ugly expression as x tends to infinity. All right, that's a special case. It's not like any of the others that we've done. And even although that's true, I'm still going to do it with essentially the same method. What do you think I should divide the top and bottom by in this question?
To e to the x.
E to the x?
Yeah. Well, let's see what we get. That's the right thing to do. It's going to come out. So you're going to have 3 over e to the x, a bit messy, plus 1. And then you're going to have 2 over e to the x plus 4. Are we happy about that? That when you divide by e to the x, it turns into that. Now we're going to do brute force, just like it was any other question. And it's going to be 3 over e to the power of infinity, add 1. And on the bottom, 2 over e to the power of infinity, add 4. So far, so good? Now, you got to think of infinity in a special way. Let's figure out what the heck 3 over infinity, e to the infinity is. Would you agree that e to the power of infinity is infinitely large? Right? E to the power of infinity is infinitely large. So isn't that 3 over infinity, which means it's 0? And isn't that the same kind of thing, also 0? So the answer is a quarter. Are we good with that? Are you happy that that makes sense, that you could take 3 over e to the infinity? That would become 3 over infinity, which we know is essentially 0. Are you cool with that? Hopefully, yeah. Here's another special case. The limit as x tends to infinity of now it does have a square root in it, but not in the usual way. That's why this is a special case. But I'm still going to do what I need to do. I'm still going to divide the top and bottom by the same thing. And you notice that we essentially just stick to finding something, you know, to divide top and bottom by when it's a fraction like this. Okay, what do you think I'm going to divide the top and bottom by this time?
Square root
Square root
of
of x.
Great. Would you agree there's only one real candidate in a question like this? Wasn't there only really one thing that would make sense, right? E to the x here. In this case, would you agree there's only one thing that's obvious, and that is the square root of x? So we'll do it. And we're going to get 81 over the square root of x, take away 1, and 9 over the square root of x plus 1. And then we can do brute force. That's the top. And this is the bottom. 81 over the square root of infinity. Eventually, what does that pop out to be?
0.
Yeah. And same for the other one. So the answer in this case is -1. Have you noticed, no matter how weird the thing looks, aren't we sticking to essentially the same process? Dividing the top and bottom by something, right? And then brute force what's left. And by the way, that particular question is like 14. I get any other weird ones? There are 2 more techniques left. One is a special version of brute force, and the other was called the sandwich theorem. So let's do the brute force ones. These questions are kind of obvious when you see them. There's not many of them, I believe. Question 20, 19 and 20 are the only two I can see right now. So you're going to find the limit as x tends to infinity of something like x cubed, take away 2x. Now, I'm calling this a special version of infinity because all I'm, brute force, is because all I'm going to do is brute force. And then I'm going to use a little bit of common sense here. When you get an expression that has no fractions in it, but you make x go infinite, would it seem reasonable that the answer is going to become some type of infinity? Maybe a plus infinity or maybe a negative infinity. Now, which one of these two do you think is bigger than the other? They're both infinite, but which one's the bigger infinite?
Infinity cubed.
Right. So if infinity cubed is a lot more infinite than 2 infinity, don't you get the answer plus infinity? If you took all the fractions in the world and just subtracted how many whole numbers, wouldn't there still be an infinite number of fractions left, right? Different types of infinity. Switch it round then. How about, because I'm seeing a lot of puzzled faces here, maybe if I do 3 of them, it'll make sense. This guy would be infinity squared, and this guy would be 4 times infinity to the power of 5. Which one of these two is the bigger infinity? Because the bigger infinity kind of wins the battle, and that's what your answer is going to be. Infinity squared or infinity to the 5? Which one's going to be bigger?
Infinity to the 5.
So if you took a number like this and you took this way, since this is going to work and it's a subtraction, can you see why the conclusion here is just negative infinity? Small, take away big, means the answer is negative. Negative what? Negative infinity. Big infinity, take away small infinity. What does that mean? It means the answer is plus. Plus what? Plus infinity. You see, in those questions, you only get 2 choices, plus infinity or negative infinity. And isn't it just based on whichever one of the two is the biggest? Okay, last fella. This one is question 21 and 22, I believe. There might be another one after that, but let's do 21. They mention in this, find the appropriate limit, and the guy that we're going to do is the limit as x tends to infinity of e to the negative 7x over cosine x. So far, so good. Now, what I'm going to do here is I'm going to rewrite that negative power like that. Negative powers are the same as the same guy in the bottom. So I'm essentially going to write this down as a fraction. Now, what the sandwich theorem does is that you take this expression and you try and figure out what the biggest it could be and what the smallest it could be. Right, let's do the cosine of x. What's the biggest number the cosine of x will ever be? What's the biggest number the cosine of x is? Can you remember?
1.
Say again?
Would that be 1?
Yes. And in this side, we find the smallest answer it could be. What's the smallest number that the cosine of x could ever be from your calc to your pre-calc 2 days? It goes up to 1, but what's the lowest it goes down to?
Is it -1?
Yeah, it is. So what the sandwich theorem does is you take the guy that you already have in the middle and you find out something that's bigger than it, right? It's always going to be this guy's bigger than it. And you find another guy that's smaller than it. And then you do this. Brute force. would you agree that 1 over 7 infinities is 1 over infinity? And 1 over e to the infinity is 1 over infinity. And isn't that 0? I could probably do that without having 4 lines. Would you agree that right-hand side is 0? Right? The limit as x tends to infinity is 0. Now, on this side, essentially you get negative 1 over e to the infinity, which is negative 1 over infinity. Nobody says negative 0. Would you agree it's 0? And then the sandwich theorem says, if the guy that you want, which is him, has to be between 0 and 0, then isn't the conclusion that the guy in the middle is 0? And so we've answered the question. The limit is 0. It's got the sandwich theorem because basically, don't you sandwich the answer between two numbers that are the same? And so the limit must be whatever those two numbers that are the same are. And this one is question 22. I think this is going to have to be our last one for today. Is sine squared x over x squared plus 8. Okay. Would you agree that sine squared x, the biggest number it can ever be, is 1 again, right? So this guy becomes 1 over x squared plus 8. And if you make this go infinite, you get 1 over infinity squared plus 8. That's 1 over infinity, and you get the answer 0. What's the smallest answer sine squared plus x can be?
-1.
Can it be -1 because you're squaring it?
Oh, no. Would it? I don't know. Would it just be 1?
Well, 0,
Yeah,
right?
it'd just be 0, yeah.
Oh, 0.
Because it's sine squared, do you agree the worst you could ever be would be 0 if you square somebody? Right, you can't get a negative. That's a bit sneaky, but the answer ends up being pretty nice. Would you agree that 0 over infinity is just overkill, isn't it still 0? So the answer in the middle is going to be 0 again. So this fella has a limit of 0. And say your last name. And while you're doing that, let me remind you a few things. Monday is a holiday, so there will be no class. I have moved the homework to be due on midnight Monday. So you've got one more day to do the homework. Online test 2 will be available at 2 p.m. today, but you don't need to do it. Probably most of you won't, I expect, until Monday midnight. So you've got an extra day to do your homework and an extra day to decide when you want to do your test. Make sense?
Yeah.
Yep, that's it then. Got your names, good. Bye-bye from now. See you Tuesday. I'll hang about for any more questions.
Have a good weekend.
You too. Have a nice weekend, everyone. See you
Thank
Tuesday.
you. Bye-bye.
Thank you.
Bye-bye.
By any chance, would you answer one of my questions on the homework?
Sure, that's what I'm here for. What you got?
It's on the second one.
What's the section number? 256?
25, yeah.
25, gotcha, okay. Hold on a second, Christian. I'm just going to find your answer to that, I'm hoping. Christian, J, A, D, B, C, D, F, G, H. Why can't I find you, Christian? Yeah, gotcha. Right, okay. I'm just opening it up. That way I'll have the same numbers that you've got. Which question number was it then? Looks like it's what?
Like all around, like pretty much 13, 14, pretty much understanding like
How to draw sketches from the information?
yeah, exactly.
Okay, so let's suppose that you were given some information about a function in terms of its limits. So its overall limit as x tends to 0 is infinity. Okay. That the limit as x tends to 4 minus, so that's our left-hand limit, happens to be negative infinity. The limit as x tends to 4 plus of the function happens to be plus infinity, which is fine. The limit as x tends to infinity of the function happens to be 2. And finally, the limit as x tends to negative infinity of the function happens to be negative 2. And all that information has to be put into the form of a graph. Now, they give you 4 graphs. So there are 2 ways of doing this. You could look at the graph and see if all these things are true. And if they are, that's the one you pick. That's the way I would do it, right? Okay. So I'm going to go and look at the graphs that you've got a choice of, and we'll see which one of those graphs has all the features that it's meant to have. Right. I don't think I hit the right one here. Are you looking at question 4 right now? I'm in the wrong window.
Actually, that's on 2.6.
Is it not?
One on. I had questions on 2.5.
Oh, 2.5. Okay. Well, that would have been a different question. I'll get out of this one and I'll find 2.5. 2.5 is in continuity. Okay.
Yeah.
Oops, wrong one. 2.5 is continuity. There we go. Christian. Why can I never find your name easily? Christian. Christian Jackson.
Oh, it's toward the bottom.
You can see it even if I gotcha. Okay.
Yeah, that one.
Yeah, you shouldn't have seen that. I should have closed the window. Too late now. I've got so many windows, so I don't know what the heck I'm doing. I've lost a window as well. Here we go. So the later ones, it looks like, is that right?
Yeah.
Okay, let's look at question 12. And I've had people with this problem before. So here is a piecewise function. Now, if you do it in Desmos, you should be able to see what it looks like. And it says, explain why this function has a problem at -4, which it clearly has, right? And the correct answer is that this overall limit is not finite. Not finite means that it could be infinite, right? That's the opposite of not finite. I wish I had someone earlier to do with the same problem, right? That that's the case. Now, you picked this one because you've seen the word finite and didn't realize, I guess, that it actually needs to say infinite. And if it was, that would be the right choice. But when something is finite, it means it's a number. And isn't this got a vertical asymptote, which is it's not finite? And I'm still going to complain to Weber saying, wouldn't it be nice if they used the word infinite and not that one? So that's all that went wrong in that one. So if we move on to the next one then, 13, you've got a piecewise function that doesn't have an infinity problem, but if you put it into Desmos, you will find that it has a jump discontinuity, I believe. Right, it's got a piece here and a piece here, right? They don't meet. And so the overall limit doesn't exist. That's one of the truths. And the limit of each is a number. Think of finite as being a number. So the limit of each is a number, but they're not equal to each other. If you do the left limit of that, you get 3. And if you do the right limit of that, you get 2 to the power of -1, which is a half. Right? And if you look at the graph, you can see a jump discontinuity, right? They're in different locations. So that's what you would do in that case. I think I should maybe show you that visually, and that might help. So if you give me a few moments to open up Desmos, we should be able to do that. Taking its good old time to do that. 151. There we go. And here's Desmos. Right. So, where in the heck am I? I'm in basic, and that's not the one I want. Oh God, this machine will drive me crazy. Here we go. You have to go out and in. Are you looking at Desmos now? Right?
Yeah.
So we had a function that was a piecewise function. So you do curly bracket, not that one, curly bracket. That's what I call those ones that look like that. X less than or equal to, what's capitals? Get that going. X less than or equal to, I think it was -1. Then you do a colon, and then you do the function. I believe, I can't remember what it was. It doesn't matter. Let's say it was 2x plus 1. And then you do enter. And you do separately, curly bracket, x greater than 1, colon, 2 to the power of x. It should have been greater than -1. There we go. Can you see there's a distinct jump discontinuity here?
Yeah.
Now, one of the things they said is that the left and right limit were finite numbers, and they are. Do you see how the left limit is -1 and the right limit is +1? Do you see that? Or +0.5, I should say. But they're not equal. And that was one of the choices that you should have picked. So they give you a list of like 4 things, and sometimes it's just one of the 4 that's right. But you could have 2 or even 3 of the 4 being right. So you read each one separately and you'd say, okay, for instance, if I gave you that and I went and said to you, the overall limit as x tends to 1 does not exist, would you agree that would be a true statement and you would pick that as one of your choices, right? The overall limit as x tends to -1 does not exist. So you look at your picture and then you answer the questions that they give you, and the ones that are true statements, you pick them. And there might be 1, but as I said, there could be 2 or even 3.
Okay.
Okay, so you look at those other ones, they're going to be pretty much the same thing. They're going to get a picture and they'll give you 4 choices. And well, you draw the picture, but then you can see from that the 4 choices which ones you should choose.
Gotcha. Thank you.
Is that it, or is there anything else you want me to do?
Yeah, I'd like to take a look at 14 again because I got into another problem with that.
Okay, 14 from what section?
On 2.6 on the web design.
Okay. Down it in space, where are you? I don't know where you are. I think I've closed the window by mistake, or I've opened it and put it somewhere where I can't find it. I'm going to assume that I've closed it. So that's going to be, if you can just remind me one more time what section that's in. And I think it's
section 2.5.
2.5.14.
Yeah, and we went over it briefly earlier, and you got me on the right track, but then I got misled by the phraseology, by the wording again.
Okay, let's have a look at.
So that brings me a question: is that, and I picked the right graph on this one, and on the graph there's a small empty hole where x equals 3. So does that mean that function is undefined?
It means it's undefined, correct. Unless, as they did here, tell you that it's equal to a number when x equals 3.
Okay, so that's what confused me about this one.
So let me show you kind of my own little picture of what that might look like and how you would interpret it. Right. So you plugged it into your calculator and it looked like this. And they told you that this guy here was equal to 3. And then there's a little hole there, right? So we would call that a removable discontinuity, right?
Yeah.
So, right. So if I went and said to you something like, does the overall limit as f of x, does that exist? And the answer, yes, it's whatever that number there is.
Yeah, because you got both ends coming to that point. Yeah, I see that.
Could I also say something like the left limit and the right limit both exist and are equal to each other?
Yeah.
And if that's one of the statements, you would say, yep, that is correct. Now, it might not, because they don't give every combination, right? Agreed?
Yeah.
Right. If I said to you, f of 1 does not exist, that's not true. F of 1 is what they told us it was. So in the piecewise function, they had something like this. It's equal to 1, or it's equal to 10 when x equals 1. I think in your case, it's x equals 3.
Yeah.
So it might say when x is 3, it's equal to 1. But when they do that, they are telling you the value of that function is 1. So it does exist. It's that dot. Now, if they'd given you the same picture, right, but no dot, right, imagine that, right, no dot, wouldn't the answer f of 3 does not exist, or f of 1, whatever the value is, wouldn't that now be a true statement because there isn't a dot anywhere? There isn't a place where you have been told the value of the function.
Okay, well, that's none of the options on 14.
Okay, so on 14, they say to you,
It says limit fx does not exist. That's not necessarily true.
that
F3 is defined, and limit f of x is finite. Again, that's not necessarily true either. And then it says F3 is undefined. That's not true.
right here, oh, wait, hold off on that one. The third one is actually the one that is true, so let's do it. It says f of 3 is defined. This is correct because they tell you that f of 3 is 1.
But limit of fx is finite.
Aha. Now,
that's
the
another part
over,
of that
yeah,
response.
well, let's do that. Isn't the overall limit of that guy where the hole is? So that does exist. It exists. It's equal to a number.
Oh, so it's a number. So that is a finite because it meets there.
Yeah.
Okay.
Every time we see the word finite, will you just replace it in your mind with a number? And that might make it a little bit cleaner in your head, because I think the finite and the infinite are, and then they go and say to you, not finite. Well, you know, that's even worse, isn't it? Because not finite is just another way of saying infinite. And so you're getting caught up in the grammar and the
Yes.
language. And so if you just replace the word finite with a number, I think you'll make more understanding of the statements as they come through. So in this case, they say that, that this is a number, but they are not equal. And that's actually correct. Isn't this guy maybe 10 and this guy is 1? Okay. They both have answers, but they're not the same answer. And that's what they said in the third dot.
Okay, so that's probably the only answer for 14.
And yeah, it actually is. It is the only answer, because none of the above doesn't work, because we know there's one answer. And f of 3 is undefined is not true. F of 3 is defined, it's equal to 1. Have we got another question?
Yeah. Do you have time for one more, or is it?
Go for it. That's what I'm
Okay.
that's what
Mine's
I paid the
number.
big bucks for.
Thanks. Mine's number 19 on 2.5. It's the second part of it. I was just
Right,
completely struggling with
let
it.
me find 19 of 2.5. And oh, I'm in the right place. Good. I don't need to change too much. The question that I've got may not be quite the same as yours, but it will be very similar. So I'll just write down what I say and you can kind of change the numbers, because I don't think I'm going to change the answer. So you've got this ugly square root. Do you have a guy that looks something like that? And then you've got an ugly cube root.
Yes.
Right, so that might be 2 and 8 and so on. If you've got the numbers that you have handy, I'll use them. That might make it a little bit cleaner for you. Do you know what? Right?
Yeah, mine is 7u minus 6 for the square root, and then the cubed root is going to be 6u minus 7.
Okay. Now, we're being asked here, using various theorems, using things you know, why this function is continuous at every number in its domain. When they say every number, in this case, it's every u in its domain. we take this function and we separate it into its two pieces. So let's look at that function. That function is the square root function. It would basically look like that if you drew it. Not very interesting, but that's what it would look like. Would you agree that this function is continuous? There's nothing wrong with it, right? And okay, it doesn't have answers over here because square root of negative numbers don't exist. But for what is there, for its domain, isn't it continuous? Now, if you did a sketch of the cube root, so it might be good, you probably would call it, you know, that in Desmos, but it's the same thing, right? If you did that guy, you're going to have to trust me. I believe it looks something like that. Would you agree that that function is continuous? There's no vertical asymptotes. There's no weird things happening. So far, so good?
Yeah.
So what we've said here is that the overall function is made up of two guys that are continuous as long as you pick in their domain. And the third one of those essentially says that. B of u is the sum of functions that are continuous on the domain. So it is continuous. So if you're made up of two pieces, right, but both pieces are continuous, the theorem says that if you add two continuous functions together, the answer function, right, the new function is also continuous. Does that make sense? If there's nothing wrong with the first curve and there's nothing wrong with the second curve, when you stick them and add them together, don't you just get a different curve, but there'll be nothing wrong
It's still
with it.
continuous. Okay.
Yeah. If one of those had a vertical asymptote, wouldn't that mean you'd have a problem?
Yes.
Right, because it wouldn't be continuous at least someplace.
And so what would, when it's asking like state the domain, is it asking?
Right. What they're asking here is, what are the usable values of this function? Now, remember that was the square root guy. Let me show you what I did here. I know that the square root function only works, you can only use it when the guy inside the square root is positive. Does that make sense? And if I solve what values of u is that true for, it ends up being that. So I know that the only values that can work with this guy is 6/7. The cube root function doesn't have any problems. You can use it anywhere. So the only restriction I've got is that I must make sure this is true so that the first bit works. And in interval notation.
Oh my gosh, the bracket. I forgot about that part. Okay. That is exactly what I had, except I had a parentheses instead of a bracket, and I remembered now.
Oh,
I know.
Yeah,
oh,
no,
that
I
is so
straight up got a problem. I got
darn close. Darn it. Yeah, I feel pain. You were there, weren't you? Really?
Yeah. Forgot about that from past math. But yeah,
41, yeah, away back in the day, yeah.
Thank you.
Okay, so are we good with that one? Any other questions, guys?
I was just gonna ask about the what's it called? The notation. Just because I was having trouble with that too. I put in a bunch of stuff that I'm pretty certain was right, but
maybe the notation wasn't
the
quite
notation
okay.
might have been messed up.
Right, let's give you some of the examples. When you do a square root, when you do a square bracket, right, I call these square brackets. This would be, you can use 3. So this would be, for instance, that's what that would get, right? If you do a curved bracket, it means you're not allowed to use 3. And so that would come from a situation like that. Infinities always use curved brackets. The convention is you can't get to infinity, so you don't do a square bracket, right? So that's the first thing. Secondly, sometimes you get an interval where it's all the numbers less than, say, negative, let's do it again. It's all the numbers, but you can't use 1 and say you can't use 3, right? So that would happen like, you know, there are a couple of vertical asymptotes and you can't use 1 or 3. Now, when you build that notation, you have to add an extra guy, right? If you're not going to use 1 or 3, you start off with negative infinity to 1, and you can't use them. Union symbol, 1 to 3, again, you can't use them. Union symbol, 3 infinity. This is a special symbol away over in that math table. It's not a capital U or even a little baby U, although it looks just like them. It's actually its own symbol. and you have to go over to, you get this little menu over here. Remember the menu that appears on the right-hand side? And you have to, yeah, you have to, I don't know where it is. I think it's under symbols, but if you go looking for it, you'll find it.
Yeah, I think I like messed up a problem like 3 times just using regular U's and then small U's, and I'm like, oh, it's over here.
Yeah. Is there any other part of that notation that you're not sure about? Does that cover most of it?
Well, it was more of like, let's see, what problem was it?
Yeah, give me a
Because
problem.
I wrote it down, but I want to
Okay.
say
If you've got it handy, just read it to me. If not, tell me what question it's in.
I got the theorem right for it, but I didn't get the problem right. So it was 6v minus 1 and then divided by v squared plus 3v minus 54.
Okay, and what will you be asked to find for this function?
Explain why the function is continuous to every number in its domain.
Right. So basically, isn't this a function with I'm not sure. 54. I'm going through my combinations of 54. 9 5s is 45. 9 6s. Okay, so
yeah, it was. Yeah, I think I got. Was it -9 and 6?
Sounds good. +9, and I would go -6 based on what you've got.
Yeah.
Here. Right. So this function has 2 vertical asymptotes, right? There's a vertical asymptote at 6 and another vertical asymptote at -9. Now, the way they get round that is by this phrase, that it's continuous on every number in its domain. So you have to go way back to 141. If I asked you for the domain of this function, it doesn't contain these 2 numbers, does it?
Yeah.
Right. And so isn't the function okay as long as you don't include these 2 numbers? So the function is okay, right? It's continuous for every value in its domain, because its domain doesn't have these 2 numbers.
So what would I write down in that box then? Because I put the huge like U.
Well, if you're meant to write down the interval, you would do -infinity up to -9, but don't include it. -9 to 6, but don't include it. Union 6 to infinity.
Oh, I think
So
I know what I did.
that's how you kick out the -9, and this one here is how you kick out the 6.
I think I know what I did wrong in this. I swapped the 9 and the 6. So
Oh,
it's
one was plus and the other was negative.
another one. Yeah, I know. I swapped the 9 and the 6 around. So let's see
Okay.
if it fixes itself really quickly.
Sure.
And was it -9? And it's right, nice.
Works.
I did have a question about like I came across a problem where there like wasn't it wasn't continuous all the way through, like it was, or like the graph had weird points in it. It
Yeah,
was
that
using
can happen.
natural logs or whatever. That one was kind of weird.
Well, the natural log has a problem when it reaches 0, because when you reach 0, the natural log of 0 is a vertical asymptote shooting downwards, and you're not allowed to use it at that point. Now, if they make life hard by sticking a value inside the log, then what that does is that it basically puts the problem to here. So that's what that would look like. So that would have a problem at 6, because at 6 the log is 0, and it doesn't exist for any other value because you cannot get the natural log of a negative number. Right? Natural logs only, just like square roots, they only exist for positive numbers. You can find the square root of 20, but you're not allowed to find a real number for the square root of -20. Similar thing happens to a log. The guy inside has to be bigger than 0, because there's a vertical asymptote when it is 0, and it doesn't exist anything else after that.
Huh.
Maybe that's why I was having a problem with 18, because it has a natural log.
Yeah,
Okay.
that's what I'm
Right.
talking about.
Okay, can you tell me whatever version of 18 is going, and we can have a look at it? What does it say for 18?
L of V is equal to V natural log.
Oh, yeah. L of V. I wish they just called everything f of x. But
I know.
anyway,
Honestly, it would be a lot easier.
L of that guy. Okay, so we got this guy.
Yeah.
Now, the problem you're going to have is this fella. So that there doesn't make any difference. It doesn't help or hinder, right? That V there you can pretty much ignore. The problem's happening here. Now, what do I know about the log function is that I know that this fella here only works when that guy there is positive. So far, so good.
Mhm.
And that guy, if I just sketch him, you get a quadratic, and you get a quadratic that goes from -1 to +1, and it looks like that. That's what 1 minus v squared would look like. So if I am only interested in this 1 minus v squared being positive, then I'm only interested in these values here. Because when v is -1 to 1, I get a positive answer for that. So that means that we should be using only values from -1 to 1. And I know it looks like a coordinate, but it's actually an interval. It's all the values will be starting at -1 and finishing at -1. So, I mean, you could look at that a different way. Wouldn't you be looking at what v gives you a v squared that's less than 1? And the answer to that would be, it has to be between -1 and 1, which is what that's saying. So you can look at it in a number of ways, but that's graphically looking at the problem. And this is looking at it, well, what makes that true? Well, that's only going to be true when this is true. And I can look at v squared and say, well, you're only going to be less than 1 in this range. Would you agree? A half squared and a minus half squared. Anything bigger than that doesn't work.
Okay.
So you might have got some benefit if I had put that guy into Desmos. I bet you I've closed Desmos again. I hope I haven't, because if I haven't, I should be able to show you. Oh, good,
Yeah,
I haven't.
This graph's kind of wonky.
Yeah, let me do that graph of that function, right? And we'll see if we can visualize why it only exists between 1 and -1, right? That's what I said. That's the only place you're going to get any meaningful answer. So I'm going to go back in here, and I'm going to get rid of this stuff because that's old stuff that we aren't using. And I'm going to turn everything into x because I'm just fed up using v's. So it's x, the natural log. Hopefully it understands that. We'll find out in a minute. 1 minus v squared. If it doesn't understand the log button, then I just need to find a button over on the right-hand side. Oops. I may, yeah, it doesn't, it looks to me like it doesn't understand it. Okay, see if you click on this little guy down here and I hit functions, I should be able to find the guy I'm looking for if I look hard enough. There we are. Do you see the LN? So I'm
That's
going to have
probably
to,
what I messed up there. I just typed in LN.
well, I was hoping it would understand LN, but evidently hoping and being true are not the same thing. Right, we got this guy. That's 1 minus x squared. Whoa, that's not 1 minus x squared. Let me kill that entirely. Right. Desmos has a bad habit of sometimes remembering things from a previous question. That's the natural log of 1 minus x squared. Is it 1 minus x squared or x squared minus 1? That's important.
I think it's 1 minus x squared.
Well, Desmos is no good. I don't know why it's not doing it. I guess if I stick an X, that's not going to make any real difference. It's just going to change the shape to that thing again.
Yeah, it does tell you it's undefined at -1 and 1 though. You get the same numbers.
Right, you get the same numbers. Well, I'm going to check something out here in case Desmos is being weird. I don't see why it should be. Oh, they're good. It done that right. Can you see the log function doing its bad things?
Yeah.
Let me try 1 minus that. Still doing bad things, right? Let me try 1 minus x squared. I wonder if. Oh, it is doing bad things. I'm just not visualizing it yet. Do you notice that on the left and right hand side at 1 and -1, it has a minus, it's a vertical asymptote? It is going down. Do you see there's nothing over here, nothing over here, no matter how I shrink it? Oh, well, okay. Eventually it gave up and it did some funny little dots. Do you see that?
Yeah.
So it gave up and said, okay, this guy's going nowhere. Where does it start and where does it finish? Well, if we go back here and we zoom right in, can you see that -1 and 1 that I was talking about?
Yeah.
So this function is a big hill and it only lives between -1 and 1. What a weird function.
Yeah, this one was giving me some weird trouble.
Yeah. So, I mean, Desmos actually took care of it. I wish I'd done a little dotted vertical line, you know, down here and there. I should be able to put that in. How about x equals 1 and make it, should be able to change its color, shouldn't you? Do you press on it for a while? Nah,
You try
not
right clicking it. I didn't do anything.
Yeah. Okay. Well, you're getting what you're getting. You're getting a vertical line. Oh, look, it's disappeared now. Oh, I did change the color to something like. There we go. It's back. And if I do x equals -1, forget about the color thing. Would you agree that they're definitely the vertical asymptotes that we were
Yeah.
worried about themselves? Just a weird function. I think that's the
Yeah.
bottom line. Okay. Well, we got any other questions?
I think that pretty much solves my issue right here.
Okay. Do you mind if I keep this as part of the lesson today so that people who go back can kind of see, because I'm sure they'll have the same questions and it may be helpful to them.
Yeah, you bet.
Okay, thank you. Teresa, you got a question?
Yeah, is there, I don't know how much more time you have, but is there any chance you could go over number like 20 or 21 in that same section?
I should be able to. Can you now remind me what section the same section is?
2.5.
2.5. 2021 coming up. At least my versions of them. It's called the intermediate value theorem question. Is that the one?
Mm-hmm.
Right. So what we're doing here, I think I'll switch over to the whiteboard now, is we're using a clever trick that kind of says this. So you've got this function e to the x, and it's equal to an equation, I should say, e to the x equals 3 take away 2x. And we're interested in the thing from 0 to 1. So far, so good. And they give you some instructions. At least these are my numbers, but yours will be similar. And they rearranged it to that, and it's still on the interval 0 to 1. So far, so good. And then you've got your first box, and you have a f of 0 equals in a box. Great. And what you have to realize is that this whole thing here is your f of x. So when you're asked to find f of 0, you're going to get e to the 0, take away 3, plus 2 times 0. And e to the 0 is 1. So 1 take away 3 gets you -2. So the value of the function at 0 is -2. So far, so good?
Mm-hmm.
Right. Then we read on a little bit later and they have an f of 1. And you might think, well, why 0 and 1? It's here and here. They're called A and B. And they got a box. And this time it's going to be e to the 1, take away 3, plus 2 times 1. And I'm doing that in a calculator because it's too hard to do any other way. If I do e, take away 3, add 2, I get 1.7. I'm not even going to be any more than that. Now, this is negative, so this is less than 0. And this is positive, so this is greater than 0. So if you can imagine putting that into your calculator, at 0, you would get an answer that's kind of down here, roughly. And at x equals 1, you get an answer that's about up here. And what the intermediate value theorem says is, oh, by the way, I put 1.7. They're just calling it E take away 1, which is the same thing, right? Since this function is continuous, would you agree that there's no way in the world it can go from here to here without crossing the x-axis? And so the next bit, it says, since f of 0 is less than 0 and f of 1 is more than 0, there has to be a number between them, c, that has the property that f of c, right, this guy, is equal to 0. And so the bit that you're missing is the box where you put in f of 0 is less than and f of 1 is more than, and there's a 0 in the middle. So if it would look something like that. And the intermediate value theorem says that if your function is continuous, right, and at one side and the other you've got two numbers, anything in between is guaranteed to happen. So somewhere the function is going to be 0, which is what that point there is. And no, that's just a location, right? That's the place. And that's called the intermediate value theorem. So if you take the second one, you're being asked to prove that that has a solution, right? Mm-hmm. And it talks about, I would probably do Desmos, but if you wanted to check that in Desmos, it would look something like this. You put in cosine x and it would look like that, right? And you put in x cubed, and wouldn't x cubed look something like that? And wouldn't it be pretty obvious that there is definitely going to be a solution, at least one, maybe some more, depends on how well I've drawn that picture. But isn't there definitely going to be one? And so in that question, they get you to set up your equation in the usual way by rewriting it like that. And then you find f of 0, and then you find f of 1. And one of these answers is a positive number, and one of these answers is a negative. And doesn't that mean then that you're going to get, in this case, I believe that one's negative, and the value of the function at 0 is positive. So because at one point it's positive and the other it's negative, doesn't that mean it has to be 0 somewhere? And the intermediate value theorem tells you that. And then it asks you to find it. I should have that. Let's do that bit. Here we go. I am going to find where this is 0. And we're going to do it by using Desmos, because that's the easiest and most obvious way for my brain to work. And I'm going to do y equals cosine of x, take away x cubed. There. Can you see the answer right there? See it being 0?
Mm-hmm.
Well, won't that be the x value where this is 0? Haven't we solved the equation?
Okay.
Right. Now, if you want to find out what the values are, don't you have to find out what 0.865 cubed is and what cosine of 0.865 are, and they'll both be the same number. One will be, cancel out the other. Is that what you're looking for? Because that's actually the last question, so I guess it is in that section.
Yeah, thank you very much. I don't know, I'm kind of getting hung up on that one. Yeah.
There are only a couple of those questions, so we don't do a lot of them, so you don't get a lot of practice at, working with them.
Yeah.
Oh, hopefully that's enough.
Yeah, I think so. Thank you. Appreciate it.
No problem. Any other questions before we call it a day? Are we good? Right, I'm going to leave yous now, and I don't think any of you will be doing the test anytime soon, but at 2 o'clock it should become visible. If it doesn't become visible for some reason or another, don't click on it, but you will see it in WebAssign. Can you shoot me an email in case I need to do something to fix it? I'm pretty confident it's going to be there. It was the last time, but just in case.
All right. You have a good weekend.
You too. Well, not too good a weekend because you should be studying for this test.
You bet.
Right.
You bet.
So just have an okay weekend.
Like an
And then
average weekend.
An average weekend and a really good one and a really good Monday when you do the test, right?
Yeah, you bet.
Okay.
All right.
Thank
I'll see
you.
you around.
See you around. Bye bye, guys.
Bye.